Now we're going to look at lemma 3 for the angle-angle similarity theorem. And this lemma is a little more complicated, so we're going to have to use the principle of mathematical induction here. And if you don't remember the principle of mathematical induction, hopefully you've seen this in one of your earlier classes. But we have a series of statements, statement 1, statement 2, statement 3, on up forever. And the way mathematical induction works, you have what's called a basis step, and you have to prove that statement 1 is true. And then we have an induction step, and you assume statement M is true, and then you use that to prove statement M plus 1 is true. And if you can do both of these things, both the basis step and the induction step, then you conclude that the statement Sn is true for all natural numbers n. So it's kind of like climbing a ladder, right? The basis step is like getting on the first rung. So if you know how to get on the first rung, we can do that. Then the induction step says, hey, if we know how to do from the first rung, we can prove that the second one's true. And if we prove the second one's true, we get the third one true. If the third one's true, the fourth one's true. And the fourth one's true, the fifth one's true. And this goes on up. So then it's how far do you go up? Well, forever, one for each natural number n. So that's the principle of induction. And so that's how you set up an induction proof. So let's take a look at our setup. So we have ABC, and we have some points. We divide this up into parts. So here I've divided up into 2 parts, or 3 parts, or 4 or 5. Let's do about 5 parts. And so what you do is you take this triangle, and we divide this side AB up into n equal pieces. And we'll call these points P1, P2, P3, P4, P5, whatever. All the way up, the last P sub n is B. Okay? And what we want to do then is so we divide it up in a certain number of parts. And so the distance from A to P1, we're going to call that Y. And the distance from P1 to P2 is Y, and P2 to P3 is Y, and so forth. So this side, we're assuming it's divided up evenly. Then we're also assuming that if we draw all these lines here parallel to the base down here, this line containing BC, then we get these other points here, Q1, Q2, and so forth. So where the line that goes through P1 parallel to the base intersects side AC at point Q1, and similarly Q2, and so forth. And so we get a betweenness relationship here that P1 is between A and P2, P2 is between P1 and P3, but we also get Q1 is between A and Q2, Q2 is between Q1 and Q3, and so forth. Now what we want to show is if these are evenly spaced here between A and B, that one thing that we want to show is that we get evenly spaced between A and C, that if this is Z from A to Q1, it's also Z from Q1 to Q2, and so forth. That's one thing we want to show. Another thing we want to show is that all of these little triangles formed are similar to each other, in particular similar to the big triangle, which means that this goes X, 2X, 3X, and so forth. So the bottom one down here is N times X, where X is the distance from P1 to Q1. Okay, so we're going to prove all that stuff. But we're going to do this by induction. So we start with our basis statement that says prove this is true for n equals 1. Well, n equals 1, there's nothing really to prove because certainly this triangle is congruent to itself. There's nothing to break down. But let's look at 2. I can also prove that. We've also already proved step 2. This is what we did in lemma 1, was basically proving this basis step for 2. 1 is trivial. And remember we drew a parallel here, made a parallelogram, showed the little triangle up here, and the one down here were congruent. and then eventually we got, since these were evenly spaced, these were evenly spaced here. Now, we want to apply the induction step. So let's say we've got several steps here, and so we want to apply the induction step. The induction step says that if we can take a triangle and divide it up into m pieces evenly on this side, then it works out. We want to show that then if you divide it into m plus 1 pieces, it'll still work where it's evenly spaced out. Okay, so if you look at this, we've got it divided up into n pieces, where n is m plus 1. Back up 1 and look at the triangle going from A to PM and of course over to QM. Remember, by the way we set it up, if we look at this little triangle from A, P1 to Q1, we know that these two are parallel, right? The line through P1, Q1 is parallel to the line through PM, QM. We know the sides on the right, on the left here, from A to PM are divided up evenly, and each one of these is going up by y. So this is y from A to P1, y from P1 to P2, and so that's m times y going all the way down to PM. So A to PM is m times y. So let me go ahead and write that. That's m times y, and the A1 to P1 is just y. So that's m steps there. And by the induction hypothesis, this is also this ratio is also m for the other side as well. Okay, so in other words, the side here from A to QM is also evenly divided up. So these are all. So the distance from A to QM is P times or is M times Z, and also the ratio here is this across here, across the bottom, is M times that one there. So it's M times X. Now, we're going to do a similar thing that we did before in the lemma. We're going to take this point P, M, and draw a parallel here. So we're given, let's see, I want to mark it parallel. Let's see if I can fix the properties on that real fast. So that one's parallel to this one here. There we go. Okay, and of course we already know that each of these are parallel. So what do we have here? We got us a little parallelogram. So we know that opposite sides are congruent there. Now we haven't yet shown that we know these are the same length, but we haven't shown yet that it's the same as Z up here. That's one of our goals. So we'll get to that in a minute. So okay. But what we do know is this distance from A to P1 is the same as from PM to PM plus 1, or down to B, in other words. So that's a Y. So we know these two purple things are both Y. So those are congruent. Okay? We also have some parallel lines. So since this line here is parallel to this one down here at the bottom, and the F property says the angle at B is congruent to this angle up here at P1. I've got it at the double mark, brown mark there. Make that a little bit bigger, maybe you can see it. Okay? And similarly, because these two are parallel, this one and this one, okay, the F property tells us that these two are parallel. So corresponding angles there are parallel. Or corresponding angles are congruent if the lines are parallel. Okay, so, of course, again, that's a Euclidean property there. And so notice we have angle, angle, side, this side over here, for this one, angle, angle, and then the side here. And so the little triangle at the top is congruent to this little triangle down here. Triangle AP1Q1 is congruent to PMBD. Now that makes this side congruent to that one, but we already know that since this is a parallelogram here, going down here at the bottom, these are congruent. So in fact, this is Z down here, and of course all of these are down in Z. And of course this is MX for this yellow one, this is MX here, and it makes X for this red one here, so that makes this one M plus 1 times X, or MX plus X, which is M plus 1 times X. And so this bottom one is M plus 1 times the X here, and since N is M plus 1, it is in fact N times X. And since this is Z, we already know it's M times Z here, so the length from A to QM is M times Z, so A to C is M plus 1 times Z, and so we get the sides are all proportional, and once again we get the distance from AB is N times Y, and A to C is N times Z, and from B to C is N times X. And so we have our similar triangles. Of course we get all of these, you can see the angles are congruent. So we have similar triangles by definition. By the principle of mathematical induction, we see that the result is true no matter what n is. So that is lemma 3 proof. Good example of a proof by induction.